Today, we have the great honor of hearing from Dr. Martin Hoffert, Emeritus Chair of the Applied Science Department at NYU, about his idea to bring the energy of the sun to Earth by reflecting it from mirrors in geocentric orbit and channeling it by lasers to a desert location. Our forum series is subtitled Technology, Its Promises and Perils. The history of technology has many examples in which promising technologies brought with them insurmountable problems. So please feel free to voice your concerns during the question period about this technology. Science laboratories, advanced technology laboratories, and he has also been a National Academy in Sciences a senior resident research associate at NASA Goddard Institute for Space Studies. He's widely published, has written on fluid mechanics, plasma physics, atmospheric science, oceanography, planetary atmospheres, solar and wind energy conversion, and many other things. His work in geophysics focused on developing theoretical models of atmospheres and oceans to address environmental issues, including ocean climate model, first employed by the UN Intergovernmental Panel on Climate Change to assess how to use fossil fuels and how they contribute to global warming. Now, I would like to introduce, without any further ado, Dr. Hoffert.
Well, let me start off by saying what a pleasure it is to address this group of particularly young people. I couldn't help gleaning the impression from all the people who were here, which is really gratifying, that wouldn't it be great if this was a kind of Woodstock of renewable energy, sort of the beginning of a movement among technologically literate young people to help us to move towards a sustainable world. The world that we're living in right now, the human-created world, which started about 200 years ago with the Industrial Revolution, has progressively enabled us to increase our population, to, on average, increase the lifespan of the average Homo sapien, and in many cases, particularly amongst those favored 20% of nations that are economically developed, have a pretty good quality of life. However, our civilization, our high-tech civilization, has been based primarily on energy derived from fossil fuel. 85% of our energy comes from fossil fuel, coal, oil, and natural gas. And we depend on that fossil fuel the way that the Roman Empire depended on slavery. Right now, we can't function without it with the currently existing technology, although many of us feel that it is urgently important to transform the technology by which we generate our energy in the coming decades to one that doesn't emit any carbon dioxide to the atmosphere. Now, if it wasn't for global warming, and this is not in itself going to be a talk about global warming, I think I should disclose at the beginning that I believe that not only is global warming a fact that's been demonstrated, it's also been predicted by myself and many of my colleagues starting back in the 1970s when I was at NASA GISS. And we have come to see it with kind of increasing horror. I mean, anyone who's ever done any research knows that if you make a prediction based on a model, it's like one of the greatest things in the world when it really works and it really happens. And of course, having created some of the models that were predicting the warming that we have been observing, the melting of high latitude ice caps, the loss of sea ice in the Arctic, with what we understand about the greenhouse effect on and what effect it's had on planetary atmospheres of our neighbors. Venus, for example, which is hotter than metaphorical hell, even though it absorbs less solar radiation than the Earth because it's very reflective, almost entirely is due to its strong greenhouse effect and the CO2 in its atmosphere. It's hot enough to melt lead. Too bad, as somebody who used to read science fiction in the 50s, I would have much preferred there to be verdant, even swamps on Venus suitable for colonization, but it was not to be. Mars, of course, we also have observed contains evidence of prior liquid water. Even now, the NASA landers, Phoenix and Opportunity, are detecting evidence of that prior water, which many of us are strongly believe was due to an earlier high concentration of CO2 in the atmosphere. And of course, our own burning of fossil fuels is part of that physical process. Without global warming, we probably would have another century to change our primary energy system. We have a lot of coal. We don't have an infinite amount, but we have probably, in terms of energy, twice as much coal as gas and oil combined. And this would really be a problem for the 22nd century. But the pace of global warming has progressed at such a rapid rate, faster than we actually thought. It brings the urgency of the problem to bear. And there are several solutions that have been proposed for alternate energy systems. I'm sure you're all familiar with solar and wind as renewable energies, geothermal, et cetera. But there are also other proposals based on green, so-called green nuclear reactors, and continued use of coal, but capturing the carbon dioxide emitted from coal as energy. The coal would be gasified and used to run a combined cycle with gas turbines and steam turbines and the CO2 buried underground. These last two ideas, carbon capture and storage, or CCS, and green nukes, are interesting topics, but I'm not going to be dwelling overly on them. I'm going to be focusing on my favorite, which is renewable, sustainable energy. And you might immediately ask, well, that's fine, but why do you want to go into space to capture this sunlight? Isn't there plenty of sunlight reaching the Earth? And I hope I'll get a chance to answer that question and some related questions in this talk. So let me first start. I'm going to try. I'm not by any chance saying I'm going to make it, but I'm going to try to finish up by 4 o'clock, and I hope that I will have stimulated by saying enough controversial things that you either don't understand or want to disagree with strongly by the end of this talk. I sometimes, when I give my talks on energy, remember some of the comics I used to listen to in the 60s who would end their shticks by saying, is there anyone I haven't offended? Probably there are going to be people offended because some of these positions that I'm going to be taking or explicating are frankly highly controversial. But that's all the more reason that we should be talking about them. Okay, let me just start by bounding the scope of the problem. I have to apologize for those of you who can't see the graphics very well, but do your best. What you see here is to kind of get an idea of the scope of the problem. And remember that I'm focusing on renewable energy, primarily solar. And I'm asking the question, are we going to be able to run our planet sustainably on renewable energy? Our civilization, roughly 6,000 years old, has increasingly been one that needs huge amounts of energy. Even if we didn't have global warming, we'd run out of coal in a few hundred years. And so Is our civilization just this brief spike, this delta function in history upon which we will, after which we will inevitably crash? Or is it possible to have a sustainable civilization on Earth? It's an open question, but it's a question that I think all of you will be vitally impacted by, and I hope many of you will devote your professional careers to solving that problem. Anyway, look at the size of this solar collector. This is not a single photovoltaic collector. It actually is an array of solar concentrators. These are basically Fresnel lenses, and you can't see it, but they're each focusing the sunlight on much smaller photoactive solar layers to save money on the solar cells, because getting inexpensive solar energy is important. But look at the size of this mother. We're talking about something that's huge. The average American consumes about 280 kilowatt hours per day. And you understand the kilowatt is a unit of power and a kilowatt hour is a unit of energy. And that's enormous. There's this, just to give you the scale of it, there's a person standing next to it. And it's pretty obvious that even if we covered up everybody's rooftops with solar collectors, we're not going to get the energy that we need. This actually comes from a review that I just wrote recently for Science magazine of a book called Sustainable Energy by McKay, who's the author. Chris McKay is a professor at Cambridge. I highly recommend this book. You can download it for free, actually. It's called Sustainable Energy. Check it out on the web. He goes through a lot of the numbers and shows where this 280 kilowatt hours per day comes from and what are the human energy consumption components of it. Okay, that's fine, but we do have enough land on the earth to collect this energy. Not necessarily in the countries. He's an Englishman, so he asked the question, can England run on sustainable energy? And he concludes no, it couldn't. But if we put these in other people's deserts, as he put it, McKay, in his case he was talking about the Sahara Desert in Africa, and transmit the power by high voltage transmission lines to England, that might be a solution. And we here in the United States have proposals about that, similar proposals to collect solar energy in southwestern deserts and augment it with wind power. And if you're interested in that, get the current this month's edition of the Scientific American and read the article by Mark Jacobson, which discusses terrestrial renewable energy. It's a very good article, but it doesn't really touch on what I'm going to be mostly talking about today. Now, space-based solar power is not a new idea. It goes back to the 70s, the first energy crisis. And in the late 60s, it was proposed originally by Peter Glaser in a paper that appeared in Science. And his idea was to put solar collectors in geostationary orbit, roughly 40,000 kilometers above the Earth, and to beam that power to the Earth with microwaves. For reasons which I hope to get into, that's a good idea, but it basically forces you to build very, very big things. Power stations that are at least a gigawatt in size. To give you an idea what that is one typical large nuclear power plant is 1,000 megawatts or a gigawatt or a billion watts of output. And that would involve a huge capital investment. And the project was dropped for various reasons. And I think it's a non-starter myself, although there are colleagues of mine who might want to still start solar power satellites with microwaves. I'm going to argue that we have another way of demonstrating the technology and starting to generate electricity that would be much less expensive and much more near term. In any case, there's growing support for space solar power, not yet in the U.S. Department of Energy or NASA, but the Pentagon recently issued a report, and you can see their recommendations were that the U.S. government should organize to allow the development of SBSP, that's space-based solar power, and conduct analyses to resolve the remaining unknowns. The problem here And they did it because it's an opportunity for strategic energy security. But the problem is neither NASA or DOD have funded programs. DOE, excuse me, that's Department of Energy. And the Department of Defense doesn't have the right mission statement. It's also interesting that controlled thermonuclear fusion, which the world has recently committed $20 billion to build a test reactor in the south of France, is a competitor technology for generating baseload electricity. And that is funded. When I say we, myself and my son, Eric, have a startup company, Versatility Energy Systems, which is here in New Jersey. And we have made a proposal to a new government agency called ARPA-E, Advanced Research Projects Agency for Energy. We haven't gotten funded yet. They so far have only accepted 1% of the proposals that they've received. But we're very enthused about it, and you'll hear something of our ideas. Okay, so what is it with this idea that it's not only the Pentagon, but at various times NASA and the Department of Energy earlier on? I did not want to press that button, so I will cancel that. What are some of the major issues here? This sounds like science fiction, collecting sunlight in space. Why would you want to collect it in space anyway? We can put solar collectors on the Earth. It's true they have to be humongous to satisfy our energy needs. And do we need some kind of a miracle, technologically, something that doesn't exist? I love this cartoon from the New Yorker. These two guys are deriving equations on the blackboard, and then there's this key step, and then a miracle occurs, and then the equations continue beyond that. How many miracles do we need? Do we need any miracles? Well, I hope to get to that. Here's just a little more on global warming. For the last 1,000 years, the temperature of the Earth for the first 900 of those 1,000 years was actually slightly cooling. And then we have this very dramatic warming that took place in the northern hemisphere, almost certainly driven by fossil fuel burning and the CO2 buildup. And the second panel shows the CO2 reconstructed from ice core data and actual measurements, which also shows that buildup in the 20th century, particularly the late 20th century. And the bottom one shows the global population building up with some key technological developments that happened along the way. I wish I had time to do this, but actually one of the courses that I taught at NYU, which dealt with technology and society, I developed this population curve for that course. But you can see all of these curves are rising in the late 20th century, and that is no accident. It's a threshold that we seem to have passed, and that threshold could lead to potentially disastrous results. We've already seen the melting of polar caps and the potential inundation by the oceans of coastal regions. And again, I'm not going to go into this in more detail now because I'm more interested in addressing the problem than proving to you that the problem exists. Well, again, I hope you can see this, but I'll try to describe it. The graph is showing on the vertical axis, they're both on the left and right. Look at the one on the right for the moment. It's power level with very big numbers here in watts, going from 10 to the 12th up to 10 to the 45th watts. And the lines that are being drawn across here, type 1, type 2, and type 3, refer to hypothetical extraterrestrial and terrestrial civilizations. The astrophysicist Kardashev was, in thinking about whether ET exists or not, said, well, one of the characteristics of an advanced civilization would be that they would continue to use more and more energy. And if you consider the type 1 civilization, it's a civilization that's using some fraction of the energy that's incident on its planet. Here we are 150 million kilometers from the sun. this pale blue dot, as Carl Sagan called it, which intercepts a minuscule portion of the energy that's radiated from our sun, 10 to the 26 watts, a big light bulb. But that is still enough energy that could allow for significant growth. You know, on this scale, because the left-hand scale is a logarithmic scale, because these numbers are so big, it breaks down into type 1 civilization, that's the planetary one, where the energy of the sun, of the central star, in our case the sun, is used to drive the civilization. On this scale, our present power consumption, which is about 12 terawatts, terawatt is a trillion watts, is about a 0.7 out of 1. But don't be misled by 0.7 being close to 1. There's still factors of 10,000 less than the solar energy incident on the Earth. So we could run our civilization with that solar energy, no problem now, if we could capture it and if we could do it cost effectively. The next type of civilization, Kardashev argued, was a type 2, which would use all the energy that's emitted from the sun instead of this little point. And he assumed that an advanced civilization would take one of their planets, break it up, and create a spherical shell around the sun. And the inhabitants would live on the inner surface of that sphere. And he actually had a practical reason for that, because the energy would be absorbed by the sphere, by those particles that made up the sphere, and re-radiated to space in the infrared part of the spectrum, so that astronomers could look for these big, strong infrared sources as potential evidence of type 2 civilizations. And these got to be called Dyson spheres. We haven't found any Dyson spheres yet, but there certainly was at least one Star Trek episode on that. And type 3 would be a galactic civilization, where all of the 80 billion or so stars in our galaxy, it's more than 80 billion. There are 80 stars for each person on Earth, and let's say there are 60, close to 100 billion stars. All of that energy would be used by the civilization. Now, that sounds like it's so mind-boggling that we can't imagine ever being anywhere near that. But yet, if you look at the two curves, the first curve, which says 2% a year, shows on this scale the rate at which our civilization would be using energy if we continue to grow in our energy utilization rate. We're growing right now about 2% a year. In not that many hundreds of years, we would be up at the type 1 planetary civilization, using most of the energy coming out of our star. And if we keep going, at least 1,000 years from now may sound like a long time, but it's not a long time compared to the Egyptians 6,000 years ago, we would need to build Dyson spheres, and it doesn't stop there, it just keeps going. And the point of this is that any kind of continued exponential growth of population and energy utilization is simply unsustainable. I mean, if we want to live sustainably on the planet, we have to find a certain level of energy consumption in a steady state, and that may be we're already at it or near it, and find a way to satisfy it. We could do that with solar energy in principle, but the fundamental hypothesis of economics, all forms of economics, Marxist and capitalist economics, where you have economies continuing to grow at constant rates, is basically unsustainable and is going to necessarily have to collapse unless we become a spacefaring civilization, and that opens up a lot of other possibilities. I have a lot of things to talk about, so I'm not going to dwell on this in quantitative detail, but I want to say that the real problem that we have to solve now is to maintain a goal of 2 to 3% per year GDP growth. And just to put this into context, in the last quarter, the U.S. economy grew about 3%, and the economies of China and India were growing at double digits. 10% or more. So those countries, as they become economically developed, are growing much faster. But if we assume that this GDP growth rate has to be continued in this century, even assuming energy efficient improvement technologies, we're going to need 2 to 3 times as much energy by the middle of the century. And if we also want to keep global warming below 2 degrees Celsius, and that, by the way, is the policy of most of the countries in the world, including this one. Obama has just said he subscribes to the U.S. not contributing to global warming more than 2 degrees Celsius relative to pre-industrial, and keeping the level of CO2 in the atmosphere below 450 or 500 parts per million. I think everyone who's worked on the problem agrees this means that we basically have to phase fossil fuels out by the middle of this century. Now, that's an incredible technological challenge because you have 2 curves going in a different direction. Emissions have to basically phase out to zero. Obama says decrease them by 80%, but that's relative to now, but that's effectively going to zero because total energy demand is going to go up by a factor of 2 or 3. So all of that is going to have to come from someplace, energy source X, even with very vigorous and aggressive improvements in the end-use efficiency of energy. This is a quantitative problem, and that's why I'm trying to explain that to you guys, because most of you have engineering backgrounds or physics backgrounds. It's a very hard problem, but it's doable, in my opinion. And let me get back to the solution, to the renewable energy solution. Of course, we have solar and wind energy, and there's enough solar, terrestrial and in space, to solve the problem. But a big problem has to do with the storage of energy. If you look in the lower right-hand corner, I hope you can see it, the solid curve is sort of a typical demand curve for an individual house or a community even. And the red curves are the variable inputs that are provided by solar and wind energy. Sometimes you have a lot more energy, even if you match the average power that you need. And sometimes you have less, and that would, of course, be the case even with this big solar collector that I showed in the first slide. So you need to match the loads, and so storage is an issue. Denmark, which is the world leader in wind power, which has 20% of its energy generation from wind, does this by backing up the intermittent wind energy with pumped storage, because they use the same electrical grid as Norway, and Norway is 100% hydro, so they basically pump the water up into the dams when they have excess power and let it run down when they need it. And of course, that means creating a new grid, because our grid is totally inadequate for doing that, and that grid would also have to have storage. And you may know that that point was made recently by President Obama, I think yesterday, about the need for the U.S. to develop a new electrical grid. The other factor here is cost. There is a conflict that's going on now between solar advocates who believe in photovoltaic cells, solar cells that convert sunlight into electricity, and solar thermal technology where the heat from the sun is focused on a working fluid that runs the heat engine. But for now, I'm going to focus mostly on photovoltaics. The arguments are not that different for solar thermal. At the National Renewable Energy Lab, this curve was developed. It's called a learning curve, or learning by doing curve, which shows historically the module price of photovoltaics. A photovoltaic module, which is not just the cells, but everything associated with the cells, including the backing and so forth. The cost is generally given in dollars per peak watt. What that means is how many watts, how many dollars does it cost to generate a watt of DC electricity when the cell is exposed to a standard illumination. That standard illumination is 1 kilowatt per square meter, or 1,000 watts per square meter, and that's because it's been standardized between different laboratories. Everybody measures it the same way. The problem is that on the surface of the Earth, the average solar radiation is only a fifth of that. It's about 200 watts per square meter over the day. So let's see what this means in terms of the cost. Right now, the cost is something like $5 a peak watt for solar PV cells. But since the real insolation or radiation at the surface of the Earth is not a kilowatt per meter squared, but 0.2 kilowatts per meter squared, the real price is about $25 per watt, per average watt. Now, compare that with the cost of a coal-fired power plant, which is less than $1 a watt or $1,000 a kilowatt. We're talking about a factor of 25. That's not a number that you're going to hear very often. And you should not think that because the cost is so much higher for solar that we're never going to get solar. And the fact is that in certain countries that want to support the development of solar energy, particularly Germany, for example, there are subsidies that are called feed-in tariffs, where when you sell the electricity back to the grid from a photovoltaic cell, they will pay you 50 cents a kilowatt hour, let's say, instead of 5 cents a kilowatt hour, which is what the electricity would cost generated by coal. That's because it's considered a social good to not generate the electricity by fossil fuel. So there is an overlap here in public policy between just taking a straight so-called economics look at it. The economics are skewed anyway because there are so-called externalities when you're figuring out the cost of a coal-fired power plant. There are pollution impacts, there are impacts on the environment like cutting off the top of a mountain and scarring it, and there are certainly climatic impacts that are not captured in the price of coal. So the point is that even so, the price of solar has to come down a lot, from $5 a peak watt to probably 10 or 20 cents a peak watt. And that's a very big factor. That's a factor of maybe 100 or something. We really need to think about that, and when we're trying to evaluate the relative merits of putting collectors in space versus the surface of the Earth. Here's another technology that people are proposing to store solar and wind energy. It's called compressed air storage. I have so much stuff that I'm going to just fly by this because if somebody's really interested, you can ask me about it. It's an untested technology. It's something that needs to be researched. And if you read the Scientific American article, you'll see that that's what they're assuming will be available for that compressed air storage for converting the U.S. to solar energy. Now, I would argue that it's a false dichotomy to pit space-based solar energy against terrestrial solar energy. The panel on the right-hand side, which I hope you can see, is the intensity of sunlight in watts per square meter versus time of day in different locations and different seasons, the summer and the winter, for example. And what you can see is in space, the energy in space is about 1,400 watts per square meter. If I took something to measure sunlight and put it in perpendicular to the rays of the sun at the top of the atmosphere, that's what I'd be measuring, 1,400 watts per square meter. But on the Earth, it's much less. It may go up to a peak of 300 or 400 watts per square meter at solar noon in the summertime, but then it goes down over the rest of the day, and of course there's no sunlight at night. So the average value, I said before, 200 watts per meter squared. There's some latitudes where it never makes it to that, but that's sort of a global average. So what we need is, if we're going to have solar power, I would argue that there has to be terrestrial solar. But for base load power, that is, power on demand, the challenges of ground solar are in many ways harder than for space-based systems. The total solar energy available at a typical site at the surface is much less than in space, and the energy varies widely with season and daily. And therefore, baseload using ground solar requires a substantial overcapacity and costly large-scale storage, or it needs a backup, which is what we have now. If you're going to put solar panels on your house, you'll probably connect to the grid by something called net metering. That means when you have no energy, you'll use the grid. So we'll really have to pay for two systems, the grid and the solar energy system. Right now, solar is such a small component, less than 1%, that it doesn't matter. But if we want to run the Earth with renewable energy, we got to think about this stuff. Now, the general principle, I'm not going to get done on time if I don't hurry up, of solar power satellites is that you have some kind of photovoltaic arrays in orbit that track the sun. The energy is then conveyed to something that beams that energy through the atmosphere, and I'll show that that can be either microwave frequencies or visible or near visible frequencies with lasers. And then it's connected to some kind of a collector at the surface that produces electricity and feeds a grid. There are various kinds of systems. This particular one is the one that was studied by NASA and the Department of Energy in 1979, and it uses microwaves, and it requires an extremely large transmitter, 1 kilometer in orbit, 10 kilometers at the surface of the Earth, and you'll see why in a minute. I am talking, and many others of my colleagues are now talking about potentially much smaller systems that can still transmit the energy efficiently from space based on lasers where the PV cells will feed into arrays of lasers and optics, and that energy is beamed to Earth. Those of you that are worried about potential military applications and that we're going to be zapping people on the surface, hold that thought. We'll be talking about that later. I just want to explain how this kind of thing works. Here's a comparison side by side. The system on the upper left, it was just recently proposed by a group of European aerospace engineers for supplying the total electrical power of Europe. It's based on a photovoltaic array in geostationary orbit. 100 square kilometers, that's 10 kilometers by 10 kilometers. It's a very big array, although it doesn't have to be, because the energy is actually beamed to the Earth with infrared lasers. Now, and I'm going to go back to this, but the system on the right is sort of the classical microwave solar power satellite, a very big collector in space, also 5 by 10 kilometers, beaming the energy to an even more humongous rectenna, 10 kilometers by 15 kilometers on the Earth. Now, there's an important physics issue here, which I'm showing in the atmospheric opacity. Opacity is the ability of the atmosphere to transmit electromagnetic radiation. And at the wavelength of visible light, where lasers would operate, and also in the near infrared, the atmosphere is pretty transparent. That's why we can look up and see the stars. And the atmosphere is also pretty transparent at the wavelength of microwaves, which is about 10 centimeters. And that's why radio astronomers can put their radio telescopes on the surface of the Earth and still see the radio emissions from stars. But in between, the atmosphere is opaque. So we have these two windows. We have a visible window and a microwave window. And the important thing is that the wavelengths are separated by a factor of 100,000. The visible and near IR is of the order of 1 micron. That's a millionth of a meter. And the microwave is of the order of 10 centimeters, which is a tenth of a meter, and that's where you get this factor of 100,000. The reason that's important is that when you transmit a beam, it doesn't matter whether it's a laser beam or a microwave beam, from an antenna or a lens and the aperture, the beam is going to spread by an amount lambda over d, lambda being the wavelength and d being the diameter. Because the wavelength is so short, you can make fairly small components with lasers that the beam will not spread. And the reason, of course, that the receiver in the case of the microwave is so big is because the beam spreads out so much, given the fact that the satellites are in geostationary orbit. Now, why should they be? Before I do that and go too deeply into that, I'm afraid I'll have to go over a little bit of 4 o'clock because there's just too much good stuff in here. I want to make it clear that this technology is something that we actually know a lot about and have done experiments on. These are 2 experiments that I'm showing here that were recently conducted in Hawaii, fairly recently in the last couple of decades, the last decade or so. On the lower left is an experiment called the relay mirror experiment, which I know some of the people involved in. In this experiment, a laser beam was projected through a telescope at a satellite with a mirror on it. The satellite was about 450 kilometers up, and it was bounced back to a receiver on the same Hawaiian island. This was done on the island of Maui, but a few hundred kilometers away. And even though the satellite was in orbit and it was moving at orbital velocity of maybe 7 or 8 kilometers per second, they were able to maintain the tracking accuracy of the beam so that the beam came down on a table, like a ping pong table, and you could see the beam as the satellite was going over, and the beam stayed on the table. Not only that, there was turbulence in the atmosphere, and there was something called adaptive optics that was employed at the telescope to compensate for the turbulence, and you could actually see the beam focus down and remain as a spot size on the table. Now, I wasn't there, but I know this has been reported in the peer-reviewed literature, and I know somebody who was there at that test and testified that this actually happened. Now, that's an incredibly accurate, it's demonstration of incredible accuracy and ability to beam lasers, and it's one of the things that we would have to be able to do. The thing we want to know is how much of that is absorbed and how efficiently can we transmit the power. Another test that was done by my friend John Mankins recently was shown actually on the Discovery Channel. The Discovery Channel a couple of months back had a series on what's called geoengineering, compensating for climate change with some kind of engineering the atmosphere. And they used microwaves, and they tried to transmit a microwave beam also from Maui to a receiver and the big island of Hawaii. What they did is they flew a helicopter through the microwave beam and measured its intensity. So there is this precedent for doing these experiments. There's also an even simpler thing to do that doesn't involve either lasers or microwaves, and that's simply to use a mirror to bounce the power from the sun onto the Earth. You start in geostationary orbit, and you can 24 hours a day have sunlight on the Earth. Now, I'm going to show a graphic soon that shows what the physics is that controls the spot size of all of these schemes, because that's the core physical idea. Anyway, the space mirror idea has also been tested. It was tested by Soviet cosmonauts on the Mir. In the final days of the Mir, they deployed the Zmadia 2.5, which was a thin film reflector, and which did, and remember this is in low Earth orbit, so the spot was moving across the Earth. It was seen in various parts of Europe. And it was the problem was the intensity wasn't that high. It was about the intensity of moonlight, and you'll see why that the intensity really has to do with the size of the mirror and the number of mirrors. So we have 3 ideas here: the simple reflecting mirror, the microwave, and the laser, and all of them are interesting. There are this thing has many ramifications. We'll try to touch various bases. Another issue that also comes up is the idea of space debris. We've launched a lot of objects into orbit, and this is an image. Look at the top one. You can see the outer ring is actually at the geostationary orbital altitude. As you know, the geostationary orbit is an orbit that goes around the Earth once every day, and if it's got the same rotational sense as the Earth, it looks like an object in that orbit looks like it's standing still. So it's a very valuable location. All of the TV satellites and communication satellites are in geostationary orbit. The other place which is very dense with orbital debris is near the Earth, the so-called LEO orbits. So we're going to have to think of that issue of orbital debris in relation to space solar power, whether it's a showstopper, whether we can mitigate that problem or even do something advantageous about it with space power. Again, this is very interesting, but I don't know if I can afford to talk about it. I'll talk about it quickly. This graph, well, let me find out if people can even see it. If they can't see it, I won't talk about it. In the back, can you see this graph? Raise your hand. In the last row. Yes, people are seeing it. Okay. So what's being plotted here is various things versus the orbital altitude. This is for circular orbits. And the first sort of between 100 and 1,000 kilometers, those are called LEO orbits, low Earth orbits. Then there are medium Earth orbits. And then at this 36,000 kilometer altitude, that's the geostationary orbit height. Now, actually, as you go into higher orbits, circular orbits, the orbital velocity decreases as you go higher. And the orbital period increases. This is a logarithmic scale. So you can read off the orbital period for near Earth orbit. It's about an hour and a half or 90 minutes. If you're in the space station, it takes you 90 minutes to go around the Earth. But as you go into higher and higher orbits, the rotational period gets longer until it gets to be a day, and then you're in geo. And if you go up, and that's at 40,000 kilometers, if you go out 400,000 kilometers, it gets to be a month. That is actually the orbital distance of the moon. That's why the moon takes a month to go around the Earth. Each of these orbits has takes more energy to get to the higher orbit. The component of that total energy that comes from kinetic energy goes down with increasing altitude, and that comes from potential energy goes up. I'm going to skip this. Okay, let me get to this because this is sort of a core idea, and I don't want to miss this. The receiver sizing is very important, and it will impact, in my opinion, what kinds of solar power satellites ought to be developed first and tested first. In the case of the mirror, what determines the spot size on the Earth is geometric optics. In other words, if I had a mirror at 40,000 kilometers, the thing that would count is the fact that the sun is an extended luminous object. It has a diameter of about 1.5 million kilometers, and it's 150 million kilometers away. And so the angle between the two limbs of the sun is preserved on reflection. And if it's 40,000 kilometers up, the spot size is 400 kilometers. In other words, the spot size is huge, and the energy that you reflect to the Earth is distributed over a very big distance, and therefore, if you really wanted to get a lot of energy, you would need to have a very large number of mirrors in space, because otherwise you wouldn't be able to collect it. It would be so diffuse. That might be a good idea at some point, because you could probably supply all the energy for the Earth if you had a mirror that was 400 kilometers in diameter in space, or if you had a combination of mirrors that added up to 400 kilometer diameter mirrors in area. But it's not going to be the first thing that you're going to try for power. And anyway, the Russians already did this, and we know that it works, but we just aren't going to get it. It's the intensity of moonlight. Moonlight is romantic, but we're not going to get power out of moonlight intensity. The microwave is the next one because the wavelength is short. It's going to project a spot size of about 10 kilometers for a 1 kilometer diameter mirror, and that's for a wavelength of 12 centimeters, 2.45 gigahertz, which is the frequency. On the laser, which has got a typically wavelength of about 1 micron, even with optics of 80 centimeters, which is less than a meter, you could make those out of a flat Fresnel lens. And even in geostationary orbit, 40,000 kilometers up, you could project 100-meter spot size, about the size of a football field. And that's something that we think we can do. We think we can do that in the near term, and it would be a great demonstration. Here's something that we're proposing to do, actually. We proposed this to ARPA-E. That's the new agency for Advanced Research Projects Agency in Energy, and we are still negotiating with them. They think it's a very controversial idea. We think it's a very near-term practical idea. We would basically use the International Space Station, which is in about a 350-kilometer orbit. You can see on the right is something I just pulled off the internet yesterday, which shows the ground track of the International Space Station. As it orbits the Earth every 90 minutes, it keeps overlapping different parts of the Earth. And one of the things this shows here is it comes pretty close to Israel. The reason I've got Israel here is I went on a visit recently to the main solar energy research center in the Negev Desert in Israel. And here's a picture of me and David Feynman, the lab director. He built this very big solar concentrator. And as we were looking at the solar concentrator, I was thinking, and the solar concentrator works by taking the sunlight and bouncing it into that focal point which has solar cells in it. We could probably do this now if we went up in the International Space Station and we had a laser, and there are diode lasers of the 100 kilowatt class. We could probably beam the solar energy as we flew over and demonstrate this and calculate what the efficiency of the power transmission would be. And it would be a great experiment to do. If it worked, we might want to follow up by lighting up a village somewhere in Africa that doesn't have any electricity. This is not something that is science fiction in the distant future. It's something that's based on actually existing technology that we would have to simply work on and try to develop into a system. I'm going to be very interested in if anyone has comments here. In our proposal, we proposed that we would start studying this by doing some experiments in the physics lab at NYU with high-powered lasers. The first laser, A, is one manufactured by a company called DLAS, which sort of stands for diode laser. And that's 2.5 kilowatts. And their spec sheet shows 50% efficiency. That's the efficiency for converting the DC electricity into coherent light. The receiver would be a photovoltaic cell, which would also be very efficient conversion of the photovoltaic light into electricity because it would transmit it very close to the band gap energy. A gallium arsenide PV cell is very closely matched to this particular laser, and we would want to do those experiments first, measuring the overall efficiency. I mean, there are unofficial claims of efficiency and anecdotal, but we want to really do a careful experiment and publish it in a journal. Very much higher power lasers are being developed for the military. The one in panel B is developed by Northrop Grumman. It's a diode pumped laser, and it was developed under this thing called the JHIPSL program, high-powered solid-state laser program. And this involves parallel chains of slab amplifiers feeding a master amplifier. And there are also other concepts, this one by Jay Penn of the Aerospace Corporation, for getting rid of the dissipated heat. People are worried about that there's so much energy coming through here, you're going to melt everything. And Jay's idea is that you use fiber optics and you bond these elements to the photovoltaic panels and they dissipate the heat to space. Anyway, there's a lot of things to study, and you can begin by studying them in the lab, and then you can study them in the field, and you can do, for example, helicopter transmissions, and eventually a space station experiment. And if everything works out, within 5 years or so, you could probably develop a demonstrator that would have a satellite mass of perhaps 1 or 2 metric tons in geostationary orbit and launch it, we estimate, for a cost in the range of $100 million, which sounds like a lot, but is peanuts compared to the $10 billion that the world is spending on the ITER, the International Thermonuclear experimental reactor. I keep pushing the wrong thing. I don't want to shut my computer down. I don't want to put it to sleep. I want to cancel it. Okay, and now. This is where that earlier experiment is. The relay mirror experiment was done at this Air Force optical station at the summit of Mount Haleakala in Hawaii. And that's more on that experiment. You also want to make the solar collectors as lightweight as possible because you have to pay the launch cost to get into orbit. And this is a company called Lagarde in California that has been putting PV cells on inflatable structures. You basically could take the whole thing and create an inflatable, rigidizable structure so that when you go into orbit, a nitrogen gas canister would inflate it, and then the ultraviolet light up there would make it rigid, and it would be very lightweight. That's another technology that could be tested in connection with this overall system. As you can see, we're talking about some existing technologies. I'm going to have to fly a little bit here. Okay. I must say, before I conclude, I'm not concluding, I'm hoping to generate a lot of questions from you guys. This kind of thing I've been working on this for a long time. In fact, back in 1979, when I first came to NYU, there was another energy crisis, and it was one that everybody felt viscerally. Bye-bye, guys, I hope you learned something. It was something everyone felt viscerally because people would have to wait online in gas stations for gas, and depending on your license plate number, you could get gas on even or odd numbered days. And there was a lot of funding then. The president was Jimmy Carter, and he had an energy program. And we were able to get funded to do a lot of things, including build a windmill on the roof of our building. This is in Manhattan, at the corner of 3rd Avenue and East 9th Street. We built a wind turbine. You probably can't see it, but in the background there were solar photovoltaic panels. It was Jimmy Carter's energy program. And then at the end of 1979, there was actually a terrible catastrophe for those interested in alternative energy. The catastrophe was, I try to stay away from politics, but Ronald Reagan was elected president. And Reagan's politics were that the government should not do anything to develop technology. Technology should be developed by the private sector, which is something I think the Pentagon would find very humorous. But that's what happened, is we lost a lot of funding. And President Obama, I believe, is talking about, although it isn't reflected yet in legislation, a new intensive alternate energy program. Myself and many of my colleagues have been working hard to influence this legislation and make sure that there's a large component of research and development, because we don't think that as the technology stands right now, it can be developed by venture capitalists. I happen to love venture capitalists. My son Eric had a company in Silicon Valley, and he has a lot of relationships with VCs. But venture capitalists usually want their money back in 3 to 5 years. They want 10 times their money back because most of their investments aren't going to pay off. And most of the really interesting stuff that we've been talking about has a longer time scale. It's longer than venture capitalists, but it's shorter than the time scale for things like fusion. And that is what we call the valley of death. Well, anyway, I was interviewed by, both of us were a lot younger, Jane Pauley, an interviewer for NBC News, and they actually gave us 20 minutes on the Today Show to talk about energy. And I believe that had we continued, that's 30 years ago, those kinds of energy R&D initiatives, we would really have something on the table now. I think it's urgent to move towards that, towards doing that now. I'm going to stop now. I could have talked about a lot of other things, but for those of you who are still here, I would love to get some questions. Thank you.